Thank you, Shomek, for introduction, and thanks the organizer for having me here. And it's always good to talk locally, so I don't have to travel. I'm going to talk about an application of the Wasserstein projection to statistics. And in some sense, it is like a special case, a case study of Jose's talk that we just listened to. And this is an ongoing work with Takeru Matsuda from the University of Tokyo and Riken in Japan. So this is an ongoing work, so there's still many things we want to know, and it would be nice to have your feedback. So the keyword is shape constraint. So shape constraints have many forms, and there are many applications. For example, in economics, let's say you have a production function. Then, if you want to say that you have diminishing return, then you want that the function is concave, or when you have a utility, you want that it is concave for investors to be risk adverse. And in this particular talk, I'm interested in a shape constraint on a probability distribution. And of course, there are also many different shape constraints. And the ones that I will focus today are monotonicity on the non-negative real line, and also log concavity. And for checkability, I will consider only the univariate case. Of course, it is very interesting to see how these will generalize to the multivariate case. But for now, we study the most concrete setup. So on the left-hand side, I show you, so by monotonicity here, I mean that there's a density which is non-increasing on R plus. And so here are a few of them. So exponential distributions is one example. And the density does not have to be very regular. So I have here an example where the density is actually piecewise constant and decreasing. And on the right-hand side, I have a few log concave distributions on R, like normal distribution, log normal, gamma, and Laplace distributions. So, and also by log concave measures, I also include the point masses. So, what's that? I include the point mass. So it's like a limit of the densities. So I'm interested in a very basic problem in statistics, which is that of density estimation. So very simple. So I have data that like x1 up to xn, and you assume that they are samples from a certain density, and you want to construct a density estimator out of the density, out of the samples. So of course, the most used estimator is the kernel estimator, which is completely non-parametric, and you have no assumptions on a density. But of course, if you have a shape constraint in mind, you may want to impose that constraint in your estimation, because if you have a kernel estimator, the weighted average may not satisfy that constraint. So given a shape constraint F, a standard approach in statistics is to use a non-parametric maximum likelihood estimation. So what does that mean? So suppose I have data, and suppose that I have a set F of the densities that satisfies the shape constraint. So let's say we have monotone densities or log concave densities. Then you simply form the log likelihood, the joint likelihood of the data. And now you think of F itself as the parameter. So the theta is the F. And when you maximize that, and if you do have a maximizer, then that is what you call the MLE in this case. So the two examples that I will discuss in this talk are very classical when you consider the maximum likelihood estimation. So for the monotone case, I think the first paper is from the 50s by Grenada. And the log concave case is, I think, may go before 90s, but I think the first one, explicit one, is in this paper. And then so the more modern development, I think, starts with this paper when they consider also the multivariate case. And these MLEs are easily implemented in software packages. Like in R, there's some packages that you can use to visualize these distributions. So here they are using the MLE. Okay, so in our talk today, I'm trying to use another objective. So namely, we want to consider estimation by the Wasserstein projection. So
So of course, by using a different loss function, this will lead to a different estimator, and we will show by some examples some differences. And so basically what we'll do in this talk is to define the estimator. We'll show some properties, and also we have some approximate numerical schemes, and then we'll show some examples, and then we'll end with some questions that I would like to answer. So before we get into the formulation, let's consider some literature that is especially motivating for me. So using the Wasserstein or a transport cost as a loss function in statistical inference has a pretty long history, but perhaps more formally it was done in this paper in 2006. So they named this the minimum Kantorovich estimator. So let's say we have a parametric, I mean, it is parametric here, but it can also be non-parametric. So suppose that you have a model, namely a collection of distributions that you want to use to model a data. So let's say in the ID case, you have data xi and you form an empirical distribution. And suppose that you have a certain transport cost loss function C, and you form the optimal transport cost T of C. Then the so-called minimum Kantorovich estimator is to find the parameter value such that the model distribution is closest to the data. In other words, you're projecting the empirical distribution on the set of models according to their transport cost. So there are many costs that are possible, but we are using the Wasserstein distance. So the use of Wasserstein distances or transport costs in estimation is now very widespread. And one very nice example is the Wasserstein GAN, where they use the Wasserstein 1 distance in the trading, and they show that it leads to very improved performance. So this paper is from a PhD thesis, and it's pretty close to our setup. So they consider not log concavity, but something called row concavity. It's a more generalized version. But actually, he did not use the projection viewpoint, which to me is much more natural. He considered a more discretization computational approach with entropic regularization. And here are some papers from the so-called information geometry community. And the idea is that if in classical statistical inference, the estimation is basically done with respect to the geometry of the KL divergence or the likelihood. And so in classical statistics, there is this Kramer-Roy inequality with efficiency and things like that. So recently, there have been some development about, okay, what are the analogs of these classical notions in the Wasserstein setting? So one example is this paper by Wu Chenlin and his students. So what he did is that is the following. So in classical statistics, we have this Fisher information matrix, which is coming from the covariance of the score function in the likelihood. So he considered instead of Wasserstein's score. So what it does, so in the classical case, what you do is that you have the log likelihood, which you differentiate with respect to each theta I direction. And then you take the covariance matrix. So in the Wasserstein score, what you do instead is that I have a probability P of theta. And suppose you go in the theta I direction. So what you do is that you transport this distribution along that direction. And then you have a potential that generates that vector field. And that potential is what you call the Wasserstein score in the ith direction. And then what you do is that you consider the covariance matrix of that score, and this forms the so-called Wasserstein information matrix. So actually, it turns out that this is basically the Riemannian matrix that the autometrics restrict to that statistical model. And one thing they did is that you can actually generalize the Kramer-Roy inequality to what they call the Wasserstein-Kramer-Roy inequality. So there is an application of the Cauchy-Schwarz inequality that you can get that there's a certain notion of Wasserstein variance, which is at least as large as the inverse of the Wasserstein information matrix. And this leads to an ongoing question about what is the difference between classical Fisher efficiency versus the Wasserstein efficiency. So my collaborator, Teklu,
with Amari and others, they consider some special cases like location scale models and in a one-dimensional case. And so last year, there is a paper by Nihad Ai. He considered what is called an information geometry of the autometric. So what they are doing is that you want to consider certain submanifolds of the space of densities, which are natural with respect to the autometric. And it turns out that at least when the parameter set is one-dimensional, the geodesic here, what they call the E-geodesic in the autometric, actually corresponds to, you can think of it as a Wasserstein version of the exponential family, and that will actually, in the one-dimensional case, attain the so-called the lower bound in the Wasserstein Kramer. So we're not, in this talk, we're not going to get to this efficiency, but I will think of this project here as a way to, as a case study where we consider a non-parametric setup, where we see some feasible difference between the classical and the Wasserstein estimators. Good. So here is the motive. I mean, the notation and the formulation. This is very standard. So because we are working in one dimension, we can consider for each distribution is quanta function. So this is the quanta function, which is a non-decreasing function from the unit interval to, let's say, the extended real line. Whether we use the level right continuous versions, that doesn't matter. What matters is that it is non-decreasing. And so in this talk, we consider Wasserstein P for P greater than 1. And this is because we have the strict convexity. When P is equal to 1, we don't have the uniqueness of the projection. So then we know that the Wasserstein distance is equal to the LP distance between the corresponding quantum functions. So we have an isometry. So again, this is elementary, but the fact that the one-dimensional, I mean, the Wasserstein space on R is flat is used in a lot of application in statistics. For example, we have the Wasserstein PCA by Bigot and collaborators. And also we have distributional time series. And also we have, let's say, entropic measure and Wasserstein diffusions that are easier in the one-dimensional case. So here's the key as the key setup in our talk here. So I want to consider a shape constraint and how to encode that. I want to have a subset in, let's say, the space of probabilities with finite p moments. In general, I can have a very arbitrary set, but to use this particular structure, I want to assume that this F is displacement convex. And also, for the well-posedness of the minimization problem, let's assume also that it is closed in the Wasserstein distance. So because we have this isometry, this is equivalent to say that if you consider the space of quanta functions of the measures in that F set, then this set is actually simply a closed and convex subset in LP. Okay, so this is very concrete. Okay, so here are a few examples. So the easiest case is the location scale family, which is studied in that earlier work by Amari and Teklu. So suppose you start with a base distribution, let's say unit, standard normal, and then you do a location scale transformation. Then that family is the location scale model and is displacement convex. So these are the two examples that we care most about, and we do these two examples mainly because they actually displacement convex. So suppose that I consider the space of monotone densities on R plus. And in this case, I need to have the finite p moment. So when we do the MLE, we do not need the moment condition, but when we do the Wasserstein, we have to fix the p as well. So it turns out that if you consider the closure of these densities, then what are the corresponding quantum functions? The corresponding quantum functions are increasing, non-decreasing, convex, and such that the limit is when the quantum probability is close to 0 is equal to 0. So this ensures that the density starts at 0. But actually, because we are doing the closure, not all densities in this, not all distributions in this set are absolutely continuous. It is possible to have a point smarts at 0, and then you have a density.
But you can also show that if you actually have data that are bounded away from 0, then the projection is always absolutely continuous. So the more interesting example is the space of the log concave measures on R. Because of the log concavity, it turns out that any log concave measure has finite moment of all orders, so you don't have to specify the P. And it turns out that this set is displacement convex. So I first knew this fact from this paper by Sant'Ambrogio and Wong. So at this point, you can already ask, why don't we do the case for a general RD? So unfortunately, the space of log concave distributions is not displacement convex. So in this paper, they constructed an example where you have one density here and another density on the line in R2. And then if you do the displacement interpolation, the support actually does not remain convex. You can have some kind of curved support, let's say when the time is 1/2. So this means that it is not displacement convex. And in this paper, they mentioned in the footnote that Yang-Hin Kim here did the one-dimensional case. But oops, sorry. But it is, so I also, as an exercise, I did myself. So basically, the constraint is that either the quanta function is constant or that it is strictly increasing and such that 1 over the derivative of the quanta function is concave. So it is not very intuitive. So for example, suppose that you consider so this is the unit interval and this would be R, the state space. So this is the quantile probability. So suppose you consider the normal distribution, okay? Then the quantile function looks like this, right? And so it is not a very intuitive shape constraint if you consider the quantile function. Okay, so then we can define very easily the Wasserstein projection. This is because we consider P is larger than 1. And so for any mu with finite peak moment, we can define uniquely the projection onto the set F. So I call this the Wasserstein projection. So F is the set on which I project to, and P is the order that I'm using. So in general, it depends on the P. And when P is equal to 1, it still exists, but it is not unique. So that is why we restrict to P larger than 1. And of course, because of the isometry, this problem is a strictly convex optimization problem. So this is good for numerical purposes, although this is still an infinite-dimensional optimization problem, so it's not completely trivial, even in this very concrete setting. And also, because of this, we have because it's a convex problem, strictly convex, we have this if and only first order condition, meaning that a particular quanta function is optimal if and only if you consider another quanta function in the same class, then the directional derivative must be non-negative. So this would be an if and only if condition. So this is the estimator. So suppose that you observe data and we form the empirical distribution that I call nu n. Then I define the estimator to be the projection of the empirical distribution onto the set. So here's a picture that summarizes everything I just described. So for any P, the space is geometrically a cone. It is basically the cone of increasing functions. And you have a certain shape constraint, which is a convex set. So I assume that it is displacement convex. And the estimator operates by projecting the empirical distribution onto the shape constraint set. Okay, so because of this, we can already, point out some interesting elementary properties of the estimator. So the first is what I call equivariance. So let's suppose that the set that you consider is close with respect to a given non-degenerate affine transformation. Okay, so then the projection and the transformation commute. So there is an extra, so there's no push further here. So for example, suppose I have a shift, then if you shift the data and then you do the estimation, it is the same as you do the estimator without the shift and then you do the shift, right? So this is also done in statistics. And okay, so this is more interesting. And when P is equal to 2, so just now I said P can be larger than 1 for any P. But the most interesting case is for statistical purposes, I think it's P equals to 2. And this is because in this case, we have the Lipschitz continuity. because in this case, the L2 space is a Hilbert space, and we get that the metric projection onto the convex set is Lipschitz, one Lipschitz. So we have that for any two distributions, the projection is actually closer than originally. And unfortunately, this is actually not true in general, because then the LP is just a Banach space, but not a Hilbert space. So this I found this pretty unintuitive, but this is unavoidable. So a nice consequence of this Lipschitz property is the following. So there are two such consequences. So the first is that even if my true distribution is not in the shape constraint set, you can still say that. So let's suppose that the data, let's say, is at this point. Then what you do is that you project both to the constraint set, and the distance between my estimator and the projected true distribution is bounded about by the W2 between the empirical distribution and the true distribution. So this means that because we know that the empirical distribution will converge to the true one, so this means that I have consistency in the sense that it will converge to the projection. So this is different from so in the classical MLE setting, basically in the specified setting, the estimator will converge to the KL projection onto the shape constraint. And here the difference is that we converge to instead the Wasserstein projection, and I will show a few examples later that will get different results. And this is especially interesting in the misspecified setting. And the second consequence is that because the right-hand side is simply the Wasserstein distance between the empirical distribution and the true distribution, there are a lot of results we can directly apply to get finite sample properties. So, and then I will show you a few examples here. So as I said, we simply have to consider the property of the W2 between empirical and the true distributions. And the convergence behavior depends in general on the regularity of the true distribution. So here, so of course, this is a very classical topic, and a lot of research is focused on actually the high dimensional case, which is important. But even in the one-dimensional case, there are a lot of things we can say. And here I'm citing a few results from this book, which is pretty recent. So for example, suppose that the true distribution has a density F and the CDF is big F. And you define this particular constant J of 2, defined this way. And this constant can be infinite. So it's non-negative, but can be infinite. It's like you are weighting the tail of the distribution according to the density. So it's like a relative importance of this. Then you can show that in all cases, the Wasserstein 2 expected value squared will be bounded above by this constant divided by n, basically. So when this J2 is finite, then you have the parametric rate. So this is the constant. But on the other hand, this is a very strong condition to say that this J2 is finite. And by the way, in the same book, they also show that for these to have 1 over n rates, it is necessary also that and sufficient that this J2 is finite. So for example, even the normal distribution does not have a finite J2, and you need a little bit stronger tail behavior for that constant to be finite. The log concave case is actually pretty nice because then you can have nice results. So for example, suppose that, so we know that the log concave distribution always has a finite second moment. Suppose you only know the sigma, which is the standard deviation, then you have a decay rate at rate log n over n. Yes. Let me see. That is correct. J2. Yeah, but then we are using the rate log n, but not 1 over n. Yeah. And a stronger condition is when it's actually completely supported, then you have the parametric rate 1 over n. On the other hand, monotonicity, as we saw in the beginning, the density may not be very regular. So we don't have we do not gain much from simply knowing that the density is monotone. Okay, so here's an explicit example which will show some differences between the MLE and the projection. Okay, so
suppose, so we know that in the one-dimensional case, for example, the MLE in the log concave case, okay, is always supported on between the minimum and the maximum points of the data. In general, it is supported on the convex hull of the data on the multivariate case. And it is log concave as log affine, the density is log affine on between the data points. So this means that you can triangulate the data and then you can do a finite dimensional optimization. So suppose that the simplest case is, okay, suppose P is equal to 2, and we have a data distribution which is 1/2 at point -1 and 1/2 at points +1. Okay, we know that in this case, the MLE is simply the uniform distribution between -1 and 1, which is very intuitive. So let me ask, what is your guess for the Wasserstein projection? Any guess? Okay, yeah, so this is the, okay, so I have an answer. So the answer is that it is actually uniform, but from -1.5 to 1.5. So what you actually get is that, okay, I have data -1 and 1, but you need to expand a little bit. You need to expand a little bit. So my intuition is that because we're doing the optimal transfer cost, and because you're doing a square, if you overshoot or undershoot a little bit, you are paying just a little bit. And on the other hand, you can get you have an overall lower cost if you do it this way. And the way it is proved, at least in my draft so far, is that I will first consider the problem where okay, because of the symmetry, right? I can consider just the right-hand side, for example. And now I will consider a relaxed problem where I just project the point mass at 1 onto the space of decreasing densities. Okay, it turns out that this is actually uniform 0, 1.5. And because this 0, 1.5 uniform distribution is still log concave, it will be optimal for the first problem as well. And this can be shown explicitly using the first order condition. So what you do is that the quantile function of my candidate is 1.5 times u, okay? And you want to show that for any other convex function in this set, this derivative is non-negative, and it is done by some elementary analysis. So it's not completely trivial. So in general, I don't have a lot of explicit examples where you can write down explicitly the projection. Okay, so now I'll show you some numerical results. And for now, I don't know how to do it exactly because it is an infinite dimensional problem, but I can do it as approximately by discretizing the quantile probability. So basically what I mean is that I discretize these points, and then I think of the quantile function as like a kind of something like a piecewise linear approximation. And for the monotone case, I can actually do a quadratic programming because the constraint can be regarded as a bunch of linear constraints, linear inequality constraints. In the log concave case, it is more complicated because I have the second derivative and so on. So but I can still use any off-the-shelf convex optimization package. Okay, so here I'll show you a few things. So first, suppose I do the same -1, 1 with equal weights, okay? I can also do for general P. What happens is that, so when P is 2, I have the 1.5, 1.5, okay? This is consistent with the numerical results. But when P is close to 1, actually you have a contraction. It is closer to the support of the data. So what happens is that when P increases from 1 to infinity, it will expand. But then it will contract as P goes to infinity. So this is pretty strange. And I don't have a very good intuition. And what is the effect of the weight? So the second thing you ask is, if instead of doing 1/2, 1/2, what happens if I have 2 points but unequal weights? So here the weight 7/8 is the weight at the point -1, okay? And then so this one has weight 1/8. So what happens is that in general, it is possible that the support, here I'm plotting the quantile functions, okay? Everything is in terms of the quantile functions. In general, it is possible that the support of the projection may or may not be a subset of a superset of the data distribution. So it can contract in one direction or expand in the other direction.
So in this case, when I have a point, like this is very close to a point marked as -1, then I have contraction in the right tail. But then as this rate increases a little bit, I will have expansion on both sides. So it will be nice from the statistical perspective to see, to quantify, let's say, the rate, like, like for example, maybe this is 1/n or 1/square of n, something like that. Okay, so, and then I'll end with the specification and some problems. So if I have, as I said, if the true distribution does not satisfy the shape constraint, then there are different projections we can consider. So in the MLE case, you have the KL projection. In our case, we have the Wasserstein projection. So here I'm showing you the result when the constraint is a monotone constraint. And let's suppose that the true distribution is a gamma distribution. So what I did here is that I have a gamma distribution chosen such that the density is unimodal, it's not monotone. So this is the quantum function of the gamma, and you sample some data, so it's approximately the gamma. And the Grenada estimator is the MLE. And it is known that the quantum function of the Grenada estimator is the convex minorant of the empirical quantum function. So it is always below the true one. So the Wasserstein one will move a little bit up, So I have another example where it is a bit more extreme. So now the distribution is a triangular distribution. And so you see a bigger effect between the two, the bigger difference between the two projections. Yeah, so this is basically it for now. As you see, there are a lot of questions I still want to consider. For example, can I have a complete categorization of the shape of the projection? So my conjecture is that the constraint has to be binding, piecewise. So I have, let's say, piecewise log concave or piecewise constant, but I don't know how to do it yet. And this could lead to exact and more efficient computation. And instead of projecting the empirical distribution, perhaps I can do entropy localization, or I can first do some smoothing, like what is done yesterday. I can smooth a little bit the data before I do the projection. And you can consider, let's say, that what is the density. I have some results based on the Lipschitz property of the Wasserstein distance, but if I want to know more local property, then I need other tools. And then other shape constraints, this is more interesting, what happens on other spaces like LD or spheres, for example. And there are other shape constraints in other setups, like in the DRO, because if I have an ambiguity set, the worst case distribution usually is somewhat irregular. But maybe if you want that the worst case distribution still has the shape constraint, you have to intersect the ambiguity set with that shape constraint set, and this will change the optimization problem. And finally, we can consider Wasserstein geometries of various shape constraint sets, like elliptical distribution or concave distributions and so on. And I think these are interesting problems. So thank you very much.